So you have your favorite problem of interest and you want to understand, is it solvable or not, and what determines that? Well, there's some systematic ways of thinking about that. And very excited to have Boaz Barak from Harvard tell us a little bit about how one might think about these things.
Thank you very much. And I have to say, I'm personally very excited to give my first in-person talk since February of 2020. And I came over right today from a 6-hour flight from Boston, so I'm giving you the full multimedia experience. You can see me, hear me, and even smell me. So that's something you cannot do for Zoom. So I'm going to give a very kind of high-level talk about some of the ideas, and I'm not going to be able to cover all of the different frameworks we have for distinguishing between easiness and hardness, and even the ones that I am able to talk to, I'm not going to be able to go into detail, but I hope to give some kind of an overview that would be fleshed out throughout this workshop and throughout this semester. So maybe the starting point is some puzzle or paradox, if you will, of the different intuitions, the different people that engage with computational problems have about what's the world look like. So complexity theorists typically say, Avi doesn't like to say that P equals NP means creativity can be automated, and we kind of believe that P is different from NP and creativity maybe can't be automated. Because so complexity theorists also say that P is different from NP. Which means that problems are generally hard. Generally, if we're talking about some optimization problems, we don't have a general way to solve all of them. Cryptographers have this very strong intuition that in some sense, an average case problem is hard unless proven otherwise. So the default state of computational problems is that they are hard. So for example, in some sense, the intuition behind the constructions of block ciphers is that if you just combine together some operations, unless you're being really stupid as a block cipher designer, you'll get something that is actually secure. So you basically just need to ensure some what they call diffusion or non-locality and some non-linearity, and you just repeat it for a few rounds and you'll get something that is secure. So basically, the hardness is the norm, not the exception. And similarly, this is kind of the intuition also behind the learning with errors problem. So it basically says, take the most basic problem that we all, learned, that our kids would have learned if it wasn't Zoom school, solving linear equations. And you just throw out, two things to rule out the most obvious algorithms. So you add some noise to kill Gaussian elimination, and you make things discrete to kill least squares minimization, and it becomes hard. And generally, that's how cryptographers manufacture assumptions on a weekly basis. And the general intuition is that you come up with this assumption, you just test out the obvious algorithm. If it doesn't work, this probably is a valid assumption. It's probably secure, and it's probably hard to solve it. And more often than not, they actually seem to work out. Like sometimes it doesn't, but more often than not, it does work out. And this is these kind of intuitions are very, seem to be very incompatible with the intuition that's of applied machine learning folks. So you've never seen, I think, an applied machine learning person that says, oh no, my objective is non-convex. Let me not even try to run it. It's definitely not going to work out. Let me try to look for something else, because there is no way I'll run gradient descent and get something good when I have a non-convex objective. No, they solve, non-convex objectives every day of the week, and it never seems to stop them. It never seems to bother them at all. And in fact, they also have the intuition, in some sense, that creativity can be automated. This is the whole kind of idea of AI, right? Creativity can be automated. So we have these kind of different perspectives on computation and maybe on creativity. And I'd like to try to say, how can we reconcile them? In particular, let's look at the two extreme views. So maybe the machine learning view is that problems are easy, except for maybe few pathological cases, which might not be that interesting in practice. So there is like a sea of easiness and maybe a few islands of difficulty. And the crypto view is that problems are hard, except for a few pathological cases where somehow the stars align and the algorithms actually work. So there is a sea of hardness and maybe a few islands of easiness. But both agree in some sense that in both regimes, both machine learning people, especially applied ones, and cryptographers agree that the algorithms that you use are sort of the obvious ones. You know, it's not as if machine learning people think the problems are easy because they really think strong and hard about which algorithm to apply to particular problem. No, you just run some kind of a gradient-based algorithm, it will work out. And similar cryptographers, they look at the 3-4 candidate algorithms, they rule them out, and they continue on with their day. They based, you know, they now use that assumption to secure the nuclear warheads and get on with their lives. Hopefully, also they get on with our lives, but with this security assumption. So in some sense, both of them kind of agree that P is different from NP. There isn't some unknown algorithm waiting to be discovered by someone that will, you know, solve all problems in the worst case. And in some sense, they also agree in some sense that creativity can be automated, at least creativity in algorithm design. There isn't this vast space of algorithms to be that you need some creative genius to discover. There is a, you know, collection of a handful of algorithms that you should try out. And if you can try out, if this works for your problem, then the problem is easy. If it's not, it's hard. Then the only disagreement is how many of them are easy and how many of them are hard. So in some sense, the way to reconcile it is to say that basically these people are just looking at different regimes. There is a space of problems, and there is some side of the space where most instances are hard, and some side of this space where most instances are easy. And cryptographers, by their very nature, they are interested in this regime where things are more hard. They have nothing to look for here. And if they find themselves here, they immediately change some parameter. So they become, so they find themselves in this regime. And if you're doing machine learning, you're interested in this area. And if by accident you find yourself in this area, well, you just ask for more data and increase the size of your model until you find yourself back in this area. So in some sense, that's maybe the intuition how you could reconcile them. But this is kind of a very hand-wavy or philosophical and probably not universally agreed upon, but let's try to look at but we'll try to talk about when are specific instances where things can be a little bit more formal. So what does it mean, the obvious algorithm? So usually we don't have really one obvious algorithm, but we have some collection of natural algorithms for optimization problems and for sampling problems. And we have this kind of general phenomena. So in many, many problems, there is some kind of a threshold where beyond this threshold, all known algorithms fail. And below this threshold, many of these algorithms work. They not always reach this. So if you have like this collection of natural algorithms, maybe some of them will be a little bit suboptimal. Some of them might be, you know, so there would be, typically there would be at least a few of them that actually reach the threshold, but maybe some that are not that optimal and fail somehow below the threshold. But it does seem that this threshold, beyond it, nothing can work. And there is some algorithm from this natural collection that matches it. That seems to be a recurring phenomena. And we'll talk a little bit about some instances of this in this talk. And I think we'll see many more in this week and in this semester. So any kind of questions, etc., about this general outline? Let's use the fact that, yes, David.
The idea that P not equal to NP is not an impediment to the algorithm, that in practice has been, even before machine learning revolution, lots of practitioners run algorithms on real life problems like integer programming problems and has been very successful. So this idea that that P not equal to NP is not impediment to practical algorithm is pretty old, no?
Right. So this is not just ML, right? This is I could have used I used ML just to be concrete, and I use cryptographers, as an example to be complete. But generally, people doing industrial optimization, they also have the same kind of view. And I think it's also for a similar reason. I mean, if they find themselves with an input that's here, they find some way to translate it here. And so if they find themselves with a problem that is hard, typically they have some freedom in modeling the problem, or again, it could be gathering more data, introducing more assumptions, doing something to the problem until they, so they have, so in another way to think about it is the following thing, that our standard paradigm, the way we teach it in undergrad class, is typically there is first a problem. The problem is given to you by God or by the instructor that gave you your exam or problem set. And you have to think hard and find an algorithm, right? That's the, I don't know, CS data structures one paradigm. So the problem is fixed, and you have to, now you have to think creatively, figure an algorithm for this problem. And the way maybe it works in practice is that you have your algorithm and you have your problem, and now you have to massage it into problem prime until you can use the same algorithm, because the algorithm is not going to change. It's always going to be the same algorithm. Like if you're doing a optimization, you're basically going to use the same kind of solver. The only question is, how do you change the problem, gather more data, do something until it can be used for this algorithm? And yeah, and there is some evidence, which arose a lot through work of people in this room, and which we'll mention, that this kind of threshold is inherent, that there really is, in many cases, you have problems that are parameterized by some parameter, and there is a certain threshold. When the parameter is, say, above the threshold, the problem is hard. When it's below, the problem is easy. Or as we'll say, it's more like ranges of threshold, and the nature of the problem also changes. But we'll see that. So what we'll talk about this, so we'll talk about inference, we'll talk about optimization, and in particular through the viewpoint of constraint satisfaction problems, in particular type of constraint satisfaction problem. And we'll talk about different tasks that you can do with these computational problems, including search, sampling, counting, decision, refutation, and planted recovery. And as you see by this long list, and it's going to be get longer, we are only going to cover kind of sample from this list. And we'll mention, although we'll not talk so much about many of those, we'll mention different algorithms or models that have been used to either solve these problems or to give evidence that they cannot be solved. And these include belief propagation, approximate message passing, local algorithms, Monte Carlo Markov chains, low-degree polynomials, sum of squares, and other hierarchies of convex programs, and a statistical query model. And I'll briefly mention, because the machine learning is obviously, practical machine learning is obviously a big deal in practice today. And while it's not the focus of this workshop, I'll try to mention of how these things, like say inference, relate to what people do with respect to machine learning in practice, at least touch on it. And one of these threshold thing, this type of threshold has been kind of observed in the past. This is not a continuous threshold, but a discrete threshold. So people have observed, and I think Eugene Lawler put it most poetically, that say there seems to be like these things where there is parameter, often the parameter is either 2 versus 3 in a lot of problems, where the version with 2 of the problem, like say matching, SAT, etc., is easy, but the version with 3 and above becomes hard. And he, in the 1970s, he already wondered, what's the reason behind this? Can we find an explanation for that? And maybe now we have a little bit of better insight than what we do and what we knew in the 1970s. And like I mentioned, the caveat is that this is going to be a bird's eye view, or like if you want a tweet's eye view. And I hope the rest of the workshop, and I think already we've seen it with Adam's talk, will be an archives eyes view, like more going into the details. And thanks to Sam Hopkins, who commented on some previous versions of the slide. He mostly gave me a lot of reference that I couldn't fit in. So he mostly helped me in being aware of what I'm missing. And
I also mentioned that I should not receive special thanks.
yes, you also mentioned that you should not receive special thanks. But let me just tell you, yeah, if there is anything good about this talk, it's all me. If anything is errors, etc., it's just Sam's fault. Okay, so what's the general setup that we are interested in? So we have some kind of a function, say I'll call it J in this talk, mapping n variables to one real number. And we can define we can think of this as the problem instance. The problem instance is a description of this function J. And now we can define all sorts of computational tasks. And generally the computational task we will be interested will be something related to minimizing J. So the search problem is to find a minimizer of J. So you want to find X star that minimizes J over some set. Think of the set as either, say, the Boolean cube or maybe the sphere. That would be the two sets we're interested in today, but generally you can think of any set. The sampling problem is to sample a random minimizer, sample a X star that is uniform among all the set of minimizers. The counting problem is to compute how many minimizers are there. The refutation problem is to prove that the minimum is at least something. That right, another way to prove that for every x in S, J of x is at least beta. The decision, or also known as hypothesis testing problem, is to distinguish. You have some alpha that is smaller than beta, and you want to distinguish between those J's where the minimum is smaller than alpha and those J's where the minimum is larger than beta. And the planted recovery is when we design some J to ensure that X star, some fixed X star that is planted is the minimizers, and we want to recover it. So we typically, in this case, JX star is designed so that X star is the unique minimizer, or any minimizer is very close to X star, and now the goal is to recover it. So these are the kind of tasks we're interested in. And again, any questions? And some examples of what J's we might be interested in include the following. So for example, if you have a SAT formula, J of psi could be the number of constraints that, so it takes as input an assignment, and the output is the number of constraints violated by X. So minimizing J corresponds to finding trying to find a satisfying assignment, or as satisfying as possible. You can have a graph, and then J will count the number of edges that are improperly colored by a coloring. So minimizing is basically trying to find the coloring. You can have a set of equations, and then minimizing is like the least square minimization. Or you can have trying to find the maximum eigenvector, or in a tensor to find the vector that's most correlated with some tensor. Or you can have, like, say, you're given a set of labeled data, and you're trying to find some X that, say, is the weights of some neural network, and you're trying to minimize the errors of this neural network. So all of those are examples of some J's that you would want to minimize, and to find the minimizer, or to know how many minimizers there are, to sample for minimizers, etc., etc., etc. Okay. And how does this relate to inference? The most kind of natural relations is the following. You have some kind of a model where you have hidden parameters, and you have some observed data. This is very much like what Adam talked about. Could be the hidden parameters, and is some W and theta, and the observed data is samples from a distribution where x1, xn that are sampled according to the Ising model, or right, the W ijx ixj. delta j xj or something like that, or in any case, you're trying to recover some parameters. So the natural j to define would be that say minus the log probability of given the observed data minus the log probability that a given x is the hidden parameter. So now basically if you're doing trying to find the minimizer corresponds to doing the maximum a posteriori probability, to trying to find the x star that maximizes the probability. You can also try to do posterior sampling, which corresponds to a sample p star such that the probability of p star is exponential in minus j of x. And more generally, you can imagine that you have some kind of a prior mu, and you want to sample p star, where p star of x is proportional to e to the minus j of x times the prior. And then in such cases, it's known that there is this variational principle that the p star is the thing that is going to, generally p star will be the thing that kind of maximizes, that minimizes the expected value of j according to, it's the, among all p's, the thing that will maximize the expected value of j and the distance in KL divergence from the prior. And this trading off this tau, so generally if you put a tau here, and this tau, the reason we put tau is if we're talking about the uniform prior, and we want to sample here proportional to minus tau inverse j, then basically the KL divergence becomes just the entropy or minus the entropy, and we are, and this is known as temperature, right? So this is like, you can think of, you have a system, and you want on one hand to minimize energy, and on the other hand, the hotter the system, which means basically the bigger tau is, you also want to have large entropy, and P star basically solves this optimization problem. Okay, so, and if we talk about generalization or just inference, so any type of say learning problem, you typically what would have is you have like some j, the ideal j that you want to optimize, which is the loss of whatever thing you're going to output on the population, and then the thing you actually have access to is not j but j hat, which is the loss on a sample. And the hope is that you'll minimize j hat, and you hope that if j hat is small and then j's will also be small, and I say small prime and small double prime because these two smalls might not be the same. Classically, we generally want to have a situation where the difference tends to 0. And in modern setting, typically we often cannot hope for that, but we hope that somehow, if you didn't do something stupid and you minimize j using natural algorithms, then you'd still have the case that if j hat is small, then j is also small, maybe not in the sense of vanishing gap, but at least if one is small, then the other is small. And all of this kind of, for us, also motivates this notion of trying to look for approximation versions of all of these things. So rather than finding the exact minimizers, maybe sometimes we just want to find x that is small, such as jx is smaller than alpha. Rather than sampling exactly from the minimizers, maybe we want to sample from this probability where the probability is proportional to e to the minus tau inverse j. So when tau is 0, then this basically is the minimizers. But when tau is non-zero, then this is somehow a soft version of that. Instead of computing the actual count, you might compute this partition function, like the sum of all of those things. And maybe don't want to find x star exactly, but at least find something that is nearby to it. So we'll also be interested, mostly be interested in these kind of softer versions. Okay, so now let me say, kind of give some intuition what's going on in this typical picture of these things. So let's just imagine that j, this energy function is like the number of violated constraints in some constraint satisfaction problem that has n equations and delta n constraints. And P star will be, proportional to e to the minus j with some, relation, some temperature as T goes to infinity, as the temperature goes to infinity, or let's say that as the temperature goes to 0, this becomes, this basically puts all of the weights on the absolute minimizers. When the temperature is not 0, then it puts the weights on some things that are near minimizers. And the set of, and let's define, say, the S star of alpha, the set of x's that j of x is less than alpha. And generally, there is going to be some relation. So P star is basically, you can think of it as the uniform distribution over S star of alpha for some alpha that depends on tau. So generally, the smaller tau is, the bigger alpha is. And what often it looks like is the following thing. Suppose we were to try to plot the entropy of P star alpha as a function of these parameters. P star tau, I should have said, but it doesn't matter. P star as a function of these things, as a function of delta, as a function of tau inverse, or as a function of minus alpha. And the behavior is generally the same. So generally, for example, if we think of it as uniform over this set, then we can see that the smaller alpha is, or in some sense, the bigger minus alpha is, the smaller this set. So the entropy decreases. Similarly, as you put more constraints, it becomes harder to minimize. So again, like the entropy will decrease. Or as you decrease the temperature or increase tau inverse, then again, you're uniform over a smaller set, so the entropy decreases. So in all of these cases, it doesn't matter what the x-axis is, it's going to look something like that. As you doesn't have to have exactly the shape, but it's going to be some monotone function which eventually hits 0. Eventually, you have no entropy left, or maybe you're only focused on one single x, and as you increase the x, the entropy decreases. And the intuition that we have is the following. So in some regime, in some regime here, as in the beginning, there are many solutions. So this set is very big, and it's also easy to find. The search problem is easy. As we continue, if we continue kind of to the limit, then in some sense, if minus alpha, for example, is too big, then solutions simply don't exist. So you cannot find them because they're simply not there. And in many computational problems, there will be some intermediate vision, which we're trying to understand, where the solutions exist, but we believe that they are hard to find. And so sometimes we would say this is the statistical threshold, and this is the computational threshold. Maybe I should also do it So sometimes we would say, okay, this is the statistical and this is the computational threshold. So at some point, solutions still exist, but they become hard to find. And at some point, you push the parameter even further, and at some point, they don't exist anymore. And then there are like other types of problems that I mentioned before, these planted or refutation problems, where suppose you continue this even further. So for those problems, for planted problems, we typically think of this P star not at a set of solution, but at a set of spurious solutions. So think of it as the background noise. So you have some set of two solutions, and say if you had a planted solution, no matter how much you increase, say for example, how much you increase the number of constraints, this solution will always satisfy it. So these two solutions will kind of always have some non-zero entropy, or non-minus infinity entropy. Let's ignore the minor things. And but at some point, the spurious solutions will disappear. So what you can think of in these cases is that there is a certain threshold, which is often known as a SAT threshold, where spurious solutions don't exist anymore. And before that, in some sense, at least here it sometimes it depends on the problem, but definitely when there is more spurious solutions than the real solutions, then you cannot recover the planted signal simply information theoretically, because the noise overwhelms the signal. So you simply cannot do that information theoretically, you can find solutions, you can find good things, but they will not be the planted thing that you look for. So even information theoretically, you simply cannot find the planted signal. If you continue this to the limit, at some point, the planted signal will be so strong that will just shout at you and say, I'm here, find me. So you'll be very easy to recover the planted signal. But again, there would be some intermediate regime where recovery is in principle possible if you had exponential time, but it is computationally difficult. So that's kind of an intuition that we have, that there is some, and generally, when we're talking about these problems for average case, then this regime is the regime where we're interested in the search problem, say sampling problem, or counting. And this is the easy part of this regime, and this is the hard part of this regime. And this regime is where we're interested in the refutation problem, say if there was no planted thing, to prove that there isn't one, or the recovery of the planted, or inference, we can also think of it as a planted problem. And here, this would be the hard regime, and this would be the easy regime. So that's kind of the general picture, that we have some intuition, and I'll try to talk about what works, try to substantiate it, and where do we find these thresholds. But maybe this is a good point to stop for questions. Yes?
Is the SAT principle obviously the same in the planted and non-planted problems?
So typically, yeah, typically the way we think of planted problems is that there is kind of a random part and a planted part. And basically the SAT threshold is when the random part doesn't contribute anymore. The random part is unsatisfiable, and the only satisfying thing that remains is the thing that you planted. Sometimes maybe what you've planted has like a little bit more than entropy, that's one solution, and then maybe information theoretically will be able to recover just a little bit earlier. But at that point, definitely you'll be able to recover. So we're going to look at two different types of problems. One of them is completely random problem, where there is no planted signal, and you just have the red curve. And another one is this planted problem, where there is these planted solutions that kind of remain there as you increase the parameter. And then there is this random part that decreases. And basically, you can think of the ratio between the red and the blue as the signal to noise ratio to some extent. Not exactly the red of the blue, but generally the parameter x kind of controls. You can think of this parameter x, whatever is our x-axis, as the signal to noise ratio. And the interesting thing is that, yes, similarly, all of those parameters kind of behave qualitatively behave similarly. You increase the number of constraints, you decrease the temperature, or you increase you decrease the threshold where you want to find a minimizer. This kind of behaves similarly. Okay. This is generally the picture, and what we're really trying to figure out, maybe one way to think about it is as a cartoon, basically. The cartoon, the statistical physicists mostly care about this line, and maybe we care about these lines where the difference, as computer scientists, we care about the difference when the problem becomes computationally hard and easy. But actually, they care deeply about this line as well, as we'll see. And this thing, I think they probably should care, but they don't really exactly have the language to do so. But we'll see that. Yes, and at some point, yeah, it's not clear how to place kind of modern machine learning problems exactly in this framework. We'll talk about it at the very, very end, I hope. So here is some very, very basic intuition. So if you have an optimization problem, intuition is that if it looks like this, it's easy. If it looks like that, it's hard. That's right. If you were to drop a marble from the top, it's pretty clear that here you will find yourself in the global minimum, and here you'll find yourself like playing Pachenko, right? So it's kind of intuitively easy that intuitively clear that the landscape of solution will change, at least for natural algorithms that kind of progress along a solution. The right thing would be much harder than the much harder than the left scenario. So in general, in this kind of, when the landscape looks like that, you'd imagine that local algorithms will get stuck at a very bad local minima, and random walks will take a very long time to converge because, you know, if you started here, your chance of getting here will be very, very small. So now let's try to make this kind of a little bit more formal. So one of the ways to try to formalize this notion of what does it mean to capture a measure that will capture when you are in the left side and when you're on the right side is this notion of overlap distribution. So suppose you have this measure P star that basically is the uniform distribution among everything that is, say, below a certain threshold. So here the P star will just be on the, like this thing here, and here it will be based on a lot of different clusters. So basically, if you do the histogram of the overlap distribution, you take two random elements from P star, and you look at, say, the normalized dot product. Yeah. Maybe I should do it like this with absolute value. So it really is between 0 and 1. Doesn't matter that much. So, so here you have basically a single cluster. So it will kind of look something like in the easy case, it will basically have something like that, right? So it's the uniform distribution over here, and everything will be, you know, most of this, it's in high dimension, most of those points will have some, I don't know, 80% overlap or whatever they have. So it will be basically something like that. And here, if you have some clusters, and let's say right now we're thinking that you have some large number of clusters, but not so large that the probability of being in the same cluster is 0, then you'll have these two different modes. So if you are in the same cluster, then you're close to each other. If you're in a different cluster, then you're far from each other. So the overlap is small. And for people who know statistical physics, this is kind of what's known as the static, say, one replica symmetry breaking. So some intuition is that this overlap distribution, this is the easy case and this is the hard case. And we'll now soon talk about some works that make it more formal. And a lot of this work is by David, who's sitting here. So let's get into a little bit more. And this is this figure from the Boaz and Kazkala. So think of, for example, some planted problems. Say a random problem, the entropy would be on the red. A planted problem, the entropy would be this purple, which kind of corresponds to both the random solution and the planted solution. And they looked at the coloring problem, but and the x-axis here is average degree, but it really is very generic, the picture that we see. So in the beginning, we basically have all solutions are in a single cluster. And in that cluster, one of them is the planted solution. So this is this kind of picture. So this is the case that this is easy for the search problem. This is very hard to recover the planted solution because it's just one among many, but it's easy for the search problem. Then, as you proceed, the landscape undergoes what they call as shattering, where basically it becomes this type of thing, where initially there are exponentially many clusters, and the planted one is one of them, and later there are only a small number of clusters, maybe at some point even a constant, and the planted one remains because it's planted. And this would be the case where the search problem is hard. But once the planted is bigger than, once the entropy of the planted kind of dominates the planted cluster dominates everything else, then recovery at least is possible in information theoretically. And at some point when you increase, in this case, it undergoes kind of a discontinuous jump. And now if there was no planted distribution, there would be nothing left. There would be, this is the SAT and SAT threshold for random instance of the CSP. And now there is nothing left. But in the planted thing, it will still be hard to recover. So recovery or of a planted signal or refutation, certifying that there is no solution would still be computationally hard until we reach some larger area where we can refute and can recover the signal. So that would be kind of the intuition. And yeah, and this is called, so this is called, when there are exponentially many clusters, you call it dynamic replica symmetry breaking. When there is only a constant number, you call static, but let's not go into the difference between those two. And basically the idea is that in this overlap, basically we think of the overlap as in the hard phase as there isn't, the overlap distribution has this gap where there is a certain overlaps that simply do not appear. And we'll see how this relates to hardness soon. So now, so now I want to just review the basic tasks that we're talking about in the algorithms, and then focus on a particular case, which is this Pspin or PXOR constraint satisfaction problems. But maybe, I don't know, maybe before that, again, like, I mean, right now we're still, I still haven't done much maps, so maybe it's still too vague to ask about, but still feel free. I mean, anything, any questions, comments, etc. Yes.
Do you have any intuition? Indeed, I think it's the case that physicists focus much less on the certification problem than the other problems.
Yes.
Do you have any intuition? Why is that problem less physical, more computer science-y than the other problems?
Yeah, I mean, one of the issues is that if we go back to this, then notice that I didn't have a drawing here because there is really no landscape of solution to talk about, right? The physicist, the planted one is kind of something new that most physicists don't know about, only these guys know. And the random one doesn't really make sense beyond the SAT threshold. There is no solution, there is no solution, so there is no landscape of solutions. So it's very hard to say, for example, for a random 3 XOR, what's the difference between random 3 XOR with 100 n constraints or n to the 1.5 constraints? Because both of them have no solution. So in terms of solution landscape, they look the same, but in terms of computational, they look differently. So I think that you really need a different language. Somehow it's clear to me that there should be a universal way to look at all of the regimes. There are similarities, and we do use similar algorithms in all of those, but the way when you focus on landscape, once you're beyond the SAT threshold, everything looks the same and looks trivial. So I think that's the challenge. Yes.
I think it's related, but also I'm trying to wrap my head around how to think about the distinction between the green and the computationally hard and computationally easy to refute in terms of the overlap distribution. Because wouldn't think it seems that already in that pink, I don't know what to call that color, right? The overlap distribution would be nice.
Yeah, so overlap I think doesn't really make sense beyond this SAT threshold. So basically, this is maybe I'll mark it. So this is the case where you ask. This is the case where you are in the search setting, and here you can talk about overlap to help you determine. So overlap can help you determine this line. Once you are here, this is the refutation setting or planted recovery. And here we don't really know, here we need something else.
So this intuition that the solution jumps at you does not, you can't see that through the overlap.
Yes, no, because the random part, the overlap distribution is kind of the distribution of solutions to the random part. And the random part is flat from this point on. So from this point on, there are simply no solutions. So you need somehow something else. And we'll talk about a little bit about what this something else is later. Yes?
But what if you add some kind of temperature parameter? Do you not still talk about the near or approximate solution?
I mean, here you can think of it as also temperature parameter. Temperature parameter will still behave very similar. So if instead of average degree, you will decrease the temperature, you will still have something very similar. Where at some point it might not be completely flatlining, but I don't think for example, in some of these problems, the point on which refutation becomes easy is way beyond anything statistical physicists care about, because for example, in 3 XOR, the refutation threshold is n to the 1.5, and the whole business with statistical physics is about constant times n, like million n, once things are like million n or n to the 1.1, any finite temperature will kind of not make a difference. So somehow I don't think solution landscape will tell you where to find this line. Yeah, maybe it will be more clear later. Maybe it will take the week or more. I mean, I think part of this. Yes.
Also, I think
yeah.
the refutation algorithm
yes.
is not syntactically defined. It's a more semantic definition. Because what is a refutation?
Yes.
It depends on what it outputs in all the other instances.
Well, but you can think of planted recovery, but and it does seem like you eventually it's true that Prasad saying that the refutation algorithm is somehow like a different problem than but in some sense it's very striking that you can use. It does seem like you use similar methods, like linear programs, etc. You could use with rounding algorithms to try to solve the problems here, and you could use with as refutation to try to solve this. And the planted thing does seem very, very similar. Like recovering the planted, in some sense, it's the search problem, but somehow it behaves very, very differently. So it's a little bit less. Yeah, it's a little bit less clear what's going on. But okay, but in any case, our intuition is that somehow, at least in this regime where we are below the, at least in this regime, where the overlap tells us when things are easy and when things are hard. So now let's just try to kind of do a catalog of algorithms and tasks. And I'll just say that, I'll try to put arrows between algorithms and tasks, but the truth is I didn't spend a lot of time on it, and you might not agree with me on all of those arrows. And part of the reason is because eventually, you can use a lot of these algorithms for a lot of those tasks, at least. So maybe there should be even more arrows. So generally, local search or gradient descent, very natural algorithms people use to find the search problem, to minimize things. Belief propagation, you can also try, or approximate message passing, AMP, you also want to use for the search problem. Sampling, classical thing to do, Monte Carlo Markov chain. Counting, you can use the Monte Carlo Markov chain. So I think also from the messages of belief propagation, you get some kind of approximation of marginals or counting. Refutation is really where convex programs naturally work for refutation, but you can use them with rounding algorithms to solve the search problem. And probably there are ways, by the way, there are usually ways, if you can do the search problem, sometimes you can also try to do the sampling problem. For example, maximize also on some random direction and output that, and maybe that will give you sampling, etc. The decision, you could use SOS, but you can also, everything that uses decision is easier than search. So everything that you could use, that search could also be used for decision. And there has been this framework, low degree likelihood, that also is useful for decision. Often it's useful to show that decision is hard. And in planted recovery, you can also try to use these low degree things. And also, there is statistical query model. I think the natural thing is to try to use that to show that planted recovery is hard, but you can also try to apply this framework for other problems as well. So some of those are algorithms that people use. Some of those are models that people use to rule out algorithms. And generally, the main point I want to convey is that there are like this collection of natural algorithms, and they all seem to have similar, even though they seem maybe superficially different, they all seem to get stuck at the same points typically. And the focus here of this in the next thing, I'm going to focus on Pspin or Pxor. It depends on whether you're a physicist or computer scientist, what you call it, problem. So now I'm going to look at specific J. So what is the Pspin case? Pspin function that you objective. Then say if P equals 2, you're trying to minimize, you are given J, which is some coefficients, some matrix. And by a matrix, you're trying to minimize Jij, Xi, Xj. And if I was Adam Clivens, I would have added some coefficient, some linear coefficient for the Xi's like he did in his talk, but I'm too lazy. So I'll just use just pure thing, Jij. And if P equals 3, then it's Jij, So you're given some tensor, you're trying to find the Xi's that minimize correlation with this tensor. And again, if I was not lazy, I would write for you also what it looks like when it's P equals 4 or 5, etc. In general, it's basically J of X. You can think of it as dot products of J and X tensor P. So you can think of J as some tensor. And for this problem, then typically we think of two cases where the case that's natural for us as computer scientists is to say, if you think of a random instance, that Jij, the coefficients are either 0 or plus minus 1, and most of the time they are zeros, and we choose the probability that they are plus minus 1, so that there will be delta n non-zero coefficients in expectation. So that's kind of the number of constraints. And so that would be like, say, a 3 XOR. If we choose this and we have this, then basically, well, each one of those is basically like a 3 XOR equation. If the Xi's are plus minus 1, then this is like a 3 XOR equation where, you get, if we're trying to minimize it, then, depending on whether this is plus or minus, it's whether we want the product of those things to be minus 1 or plus 1 or similar. If you thought of them over GF2, whether they want the XOR to be 1 or 0. And sometimes we also think of those as normal with some standard deviation. And generally, we can also think of the X's as being either, let's say, the sphere or plus minus 1. So when 2, if you're minimizing over the sphere, then this is basically 2 XOR. This is strongly related to maximum cut and also Sherrington-Kirkpatrick model. So all of those basically are different names for this problem of minimizing this when for random J and over the Boolean cube. If you're just minimizing over the sphere, then if J is just a matrix in P equals 2, then you're just trying to find the minimum eigenvalue, which is something we obviously know how to do. So in the case of the 2, there is a difference, although we'll see maybe the difference is not as big, because in the random case, maybe this is obviously easy, but this turns to be also easy, just less obviously so. In the 3 and above case, then this is K-XOR, and this is basically tensor maximization. Both of them are, just switch the sign, minus J or J. And this is, or injective tensor norms, sometimes known. It's also useful in quantum information theory, etc. And generally, as we'll see, this side is easy, this side is hard, as in that quote by Eugene Lawler. And maybe this would be a good place to take the break. It's a little bit earlier, but is that okay? Yes. So maybe if there is any question about it. So we'll try to talk about some evidence on where things become hard and easy in this problem. So why, for example, the 3 and above is hard and the 2 is easy. Question, yes?
You could consider a mixture of the 2 and 3.
What?
You could consider a mixture of the 2 spin and 3 spin.
We will.
Okay.
We will consider, because actually that's easier for me. I mean, there is a very complex paper of Montanari that shows that the SK model, random SK model, is solvable in polynomial time, you know, so with the Q2, but it's actually much easier to consider the mixture and then move to the sphere case, where there is an easier paper, a predecessor paper of Subag, and that's where actually the result we'll talk about. Okay, so we'll take a break.
Perfect. Yeah. So we'll be back here in exactly 20 minutes, 3:15.